Oh yeah, I should say that at the end of the week, I will always put a summary on the layer, and the summary is a Word file consisting of 8 or 10 pages, which is quite comprehensive. I'm writing out my whole lecture, so that should be of great use to you. At least the students in the past few years were very enthusiastic about these summaries, and I trust you will be too. Okay. So we're also, well, we're not all psychologists, but we're doing a research master in the field of psychology, or some subfield of psychology. And in psychology, well, there's a strong experimental tradition. Psychologists like doing laboratory experiments, which may be either covering, dealing with between subject designs, where we have different people in different groups, or within subject designs, where we observe the same group of people under different conditions. And of course, in experiments, we usually focus on just a few dependent variables and also relatively few independent variables, which everything can be strongly controlled. Alternatively, we may be dealing with observational studies, relational designs, where we have a large sample of respondents, and we have a lot of measurement instruments, questionnaires and such for measuring our variables. When we are dealing with a quantitative dependent variable, then in the case of experiments, we're usually working with some sort of an ANOVA design, or a small extension of that known as ANCOVA, which we'll also be reviewing in the 4th week. When we're dealing with observational research, we usually work with regression models. As we shall see, regression analysis and analysis of variance are really two sides of the same coin. It's not really two different models, but they are the same models with using different parameterization. Now here today we will be looking at an example taken from social psychology, which was done by Hugo Alberts, Caroline Martijn, and a few people that I do not know. And they reported their research in an article, Carrying on or Giving In, the Role of Automatic Processes in Overcoming Ego Depletion. To make sure that I give you the necessary background details, I'm going to read this out loud, but I won't be reading out loud anything for the remainder of the lecture, so don't get worried. The studies by Alberts and his associates focus on ego depletion, which is the finding that self-control seems to be drawing on a fixed and limited resource, akin to strength or energy. After an act of self-control, the resource becomes temporarily depleted, leaving the individual in a state of ego depletion. There is evidence that people distinguish between two classes of beliefs about exercising self-control. The first class of beliefs characterizes self-control as energy. People believe that they have only a limited amount of energy available for their self-control operations, and that they are likely to fail when demands are too high. Furthermore, for optimal performance, one needs to be well rested and free of other self-control demands. The other belief is that self-control is primarily a matter of motivation. If you really make an effort, you can do much more than you think. Alberts and his associates carried out 3 related studies that rest on the idea that people, when faced with a series of control-demanding operations, expect and act upon the implicit belief that self-control consumes energy. Therefore, subsequent exercise of self-control will result in impaired performance. Alberts wanted to test whether self-control performance can be increased when the alternative implicit belief, self-control as motivation, becomes more accessible. To the extent that self-control performance is sensitive to implicit theories about self-control, activation of the self-control as motivation belief should reduce or even eliminate the effect of ego depletion. If, on the other hand, perseverance of self-control primarily depends on the amount of effort already exerted, then activation of this belief should not affect subsequent self-control efficacy. The aim of the study that we will now be discussing was to investigate whether the activation of self-control as motivation improves people's self-control performance. The first part of the study consisted of the manipulation of initial self-control induced by presenting participants either with solvable but extremely difficult labyrinths, high self-control, or relatively easy labyrinths, low self-control. The second part of the study intended to increase the salience of self-control as motivation by means of priming. To do so, half the participants were presented with a scrambled sentence task. We're going to look at some examples in a moment, including sentences related to perseverance, holding on, and so forth, whereas the other half received scrambled sentence tasks with neutral sentences. The third task of the study was a physical stamina task and consisted of squeezing a hand grip. Although squeezing a hand grip seems primarily a matter of muscular strength, it has proven to be a successful measure of self-control in prior research, because squeezing a hand grip becomes fatiguing after a short period of time. The person feels the urge to stop squeezing. Overcoming this fatigue and overriding the urge to quit requires self-control. In order to be able to control for individual differences in hand strength, hand grip performance was measured twice, before the labyrinth task and after the scrambled sentence task. Differences in performance on the first and second physical stamina measure forms the main dependent variable. Okay, so that's the background. I hope you've all been paying attention. So now we're going to have a closer look at this research. First of all, the priming manipulation. So these were the scrambled sentence tasks. All participants received a total of 25 4-word sentences, which they had to convert into correct 3-word sentences. In the neutral prime conditions, these were sentences like tea Nicole makes in, which should be converted to Nicole makes tea. And then in the perseverance prime condition, we had sentences like holds Peter on thee, which could be converted into Peter holds on. Okay, then of course we had the labyrinth task. This is an example of a difficult labyrinth, and if you look at it long enough you will start to get a headache, and it's quite unsolvable. So you have to work on this very hard, and at some point of time the researcher says, okay, thanks, stop, that's enough. In the easy labyrinth condition, they had much smaller labyrinths which could be easily solved. So after solving one labyrinth, you got the next one, and then the next one. It wasn't very demanding. Okay, so we had, actually this was a two-way design. We had two independent variables with each two levels. We had either difficult or easy labyrinths, and we had either the neutral prime or the perseverance prime. And it is of course possible to consider this as a one-way design consisting of 4 groups. In that case, the first group had the difficult labyrinths and the perseverance prime. The second group, difficult labyrinths plus the neutral prime, and we had 2 other groups in the other 2 conditions. Now, so this is what Alberts and his associates did, and they collected a lot of data, of course. And after collecting the data, the first task is to become acquainted with the data, or as the methodologist Rosenthal calls it, make friends with your data. So this is a histogram showing the distribution of the dependent variable, which I have called here post-squeeze. We're squeezing the hand grip. We did that in a pre-test, and we did it in a post-test. So these are the results of the post-test, and therefore I've got this post-squeeze in seconds. So we can see that there was one subject to the left who didn't quite get the idea, 0 seconds, and all the way to the right we can see that there was one particular person who succeeded in squeezing the hand grip for over 2 minutes. Most of the subjects, however, succeeded in squeezing the hand grip for about 40 seconds. Now, it's obvious, of course, by looking at the histogram that this particular distribution did not come from a normally distributed population. That may not be a problem, but we note it nonetheless. And we can also see that there are two tests of normality, which both tell us, a Mogorov test and a Shapiro-Wilk test, they both tell us that the null hypothesis that this particular distribution comes from a normally distributed population should be rejected. In all likelihood, the population will be skewed to the right. And of course, that is perfectly understandable because this is a task which demands considerable muscular strength. As we all know, there's a small proportion of people who are very strong indeed, so you are likely to see a distribution like this. Now, then we have a box plot for getting a quick impression of whether or not there were any outliers in the box plot. Of course, we can see the lower part of the box. I forgot my pointer, sorry. The lower part of the box corresponds to the first quartile. The upper part of the box corresponds to the third quartile. The first quartile is, of course, the score for which we can say that 25% of the participants had a score which was actually lower than that particular score. The upper part of the box tells us this is the score for which we can say that 75% of all participants had a score lower than this particular one. And the thick black bar in the middle of the box corresponds to the median, so that's the point, so that's the particular score for which we can say that 50% of all the participants scored below that particular score, and the other 50% scored above that particular score. Now, the antennae that you can see below and above, they go to the minimal score and the maximal score that were no outliers. So this particular bar corresponds to the lowest score that was observed, but it was no outlier. At the upper part you can also see a bar which corresponds to the largest score that was observed that was no outlier. And then of course we can see two small circles above the upper antenna, and these two circles correspond to outliers according to a particular criterion known as the 1.5 times IQR criterion. So looking at a box plot, you can easily observe whether there were any potential conspicuous outliers, and there may be two outliers according to the 1.5 times IQR criterion. So by looking at a table like this, which summarizes the extreme values, we can see whether these actually were outliers. There are outliers, of course, if the particular scores concerned really differ from the next lowest or the next highest score. You can see in the table with highest scores that the highest score was 129, the next highest score was 128, so a gap of 8 points. And then the next was 112, gap 9 points. Well, these are all considerable gaps, so these are truly somewhat outlying observations. Okay, so like I said, the skewness doesn't come as a surprise. And Albert, of course, realized that subjects would vary greatly in their physical strength. And so a pretest was taken, and the dependent variable was the difference post-test minus pretest, or a gain score. And if you look at, here we have a table with descriptive statistics for the 4 different groups, difficult and prime, difficult and not prime, etc. And we can see immediately that the lowest score, this is a relatively bad performance. The lowest score is to be found in the condition where we were faced with difficult labyrinths, so we were ego depleted, so to speak, and we were not primed to hold on. In that case, the pre-test score was much better on average than the post-test score. So obviously this is what we would expect given the phenomenon of ego depletion. On the other hand, we can see a relatively high positive score in the opposite condition where people were faced with easy labyrinths, so not much ego depletion there. And on top of that, they were primed to hold on. And in that case, they were, on average, successful in doing better on the post-test than on the pre-test. And the other two conditions were more in the vicinity of 0, so about similar performance in the post-test as the pre-test. Looking at the standard deviations, we can see that it looks like the variability in individual scores is largest in the two conditions where people were faced with easy labyrinths. So if they were faced with difficult labyrinths and they were depleted, there's less scope for variability in the scores, obviously. So now we're going to look at the four groups separately and see how the dependent variable, pre-test minus post-test, is distributed in the separate groups. This is of some importance because, as I told you in the beginning, when performing an experiment like this, we will usually be using an analysis technique known as analysis of variance. And to be able to use that particular technique validly, the assumption is that the various samples, we have four groups, so we consider these as four different samples taken from four populations, that all these samples come from normally distributed populations. That is one of the assumptions of the analysis of variance technique. And on top of that, another assumption is that the variance, the variability of the scores within the various populations is equal. Okay, so we're trying to get an impression of whether or not these assumptions are actually met. So here we have the group that was faced with difficult labyrinths and which was primed to hold on, and we can see that the distribution of scores is fairly symmetric. Nonetheless, we can see that the normality tests indicate that it is not likely that this particular distribution is coming from a normal distribution, and as we shall see, that has to do with the fact that there are relatively, that many of the scores seem to be grouped in the middle, more than you would expect in a normal distribution. Here we have some additional descriptive measures, like a skewness statistic at the bottom of the table. And the skewness, if we have a perfectly normally distributed population, the skewness should have the value 0. If we have a value which is smaller than 0, this indicates a distribution skewed to the left. A value larger than 0 indicates a distribution skewed to the right. And here, of course, we have the value 0.43, and that indicates that this particular distribution is somewhat skewed to the right. It's barely observable. You can use this particular information as a sort of a significance test by, let me use the visualizer, by forming an interval like the skewness as observed in the sample, skewness, plus or minus 2 times the accompanying standard error. And if 0 in the interval, then accept the null hypothesis that the sample is drawn from a normally distributed population. So this is a rough way of carrying out a significance test. If we do that with these particular numbers. We can see we have a skewness measure of 0.43. Now, if we take 2 times the standard error, which is reported in the next column, that's about 0.51. So 2 times 0.51 is about 1. And so if we have 0.43 minus 1, then we have a negative number. And if we have 0.43 plus 1, we get a positive number. So we have an interval which contains the value 0. So it would be reasonable to adopt the null hypothesis that this particular sample of observations has been drawn from a normally distributed population. Then we have the final measure, which is known as kurtosis, which tells us how flat a particular distribution is relative to the normal distribution. If you have a perfectly normally distributed population, the kurtosis will equal 0. If you have a negative kurtosis, then the distribution is somewhat flatter than would be expected under a normal distribution, and if it's positive, you have a distribution which is more peaked than you would expect for a normal distribution. Now, in this particular case, we can see that we can also use this particular number, 2.1, plus or minus 2 times the accompanying standard error, so that's about 2. And if we form an interval by taking 2.1 minus 2, we get a lower number which is positive, and we get an upper number which is also positive, so the value 0 is not in that particular interval, and that accounts for the fact that the normality tests indicate that it is unlikely that this particular distribution comes from a normally distributed population. It has to do with the fact that this particular distribution is more peaked than you would expect. Okay, so these are a few statistics that you can look at in order to get an idea of whether or not it's reasonable to assume that at population level this particular distribution will be normal. Here we have the box plot. I just explained that these circles indicate that we may have an outlier according to the 1.5 times IQR criterion. We also see a star above, and the star indicates a even stronger outlier. That's an outlier according to the 3 times IQR criterion. So that if you see a star, that means that we really have an observation that is conspicuously large or conspicuously small. Okay, now here we have the second group, which looks perfectly normal, I'd almost say. Same goes for the accompanying box plot. The third group, which shows somewhat of a gap on the left side of the distribution. And here we have the fourth and final group, which also shows a gap on the left part of the distribution. And if you look at this particular distribution, you can see that actually the scores are strongly peaked around 0, and of course we have a somewhat a tendency towards the left, which is probably because we have an outlier there. And if we look at these skewness and kurtosis measures, this is immediately reflected. The kurtosis is the skewness is strongly negative, suggesting a distribution skews to the left, and the kurtosis is strongly positive, meaning that it is relatively peaked and relative to a normal distribution. Okay, so, and here we see in the box plot that the lowest score is a strong outlying observation. It pops up as a star in the box plot. Now, if we have potential outliers, we have to decide whether or not to retain the outliers in our analysis or whether to take them out. Outliers can have a distorting influence on summarizing statistics like the mean and the standard deviation. So we have to think carefully about that. Outliers may be indicative of coding errors, or they may be indicative of observations that don't really belong to the population that we wish to generalize to. If you have a reaction test and there's one particular person having a very slow reaction time, we're going to look at some background characteristics of this particular person, and lo and behold, whereas all the other participants are about 20 to 25 years of age, this particular person is 60 years of age, and that has probably to do with the fact why he is so slow. So then immediately you conclude that this particular person is not representative of the population that you want to generalize to, so you are well, you have every reason to take that particular observation out. But you cannot do that automatically. You have to look at background characteristics of potential outliers before you decide to take them out or not. Now, to get an indication of whether an outlier is truly an outlier, you may convert the raw scores, so the difference in seconds between pre-test and post-test, into z-scores, because the z-scores give us immediately an indication of whether or not a particular score really was extreme. If we look at the first group, which was faced with difficult labyrinths and was primed to hold on, we can see that the most extreme score on the left side corresponded to a z-score of minus 2.11, and the most extreme score on the upper side corresponded to a z-score of 2.46. In the second group, we can see that the lowest z-score was minus 1.97 and the highest score was 2.26. The third group, minus 2.64 and 1.77. And the last group, minus 3.5 and plus 1.57. Now, you all know the standard normal distribution, of course, and you realize that you may expect to find about, if you have a large collection of observations, you would expect to find about, in this case, 4 z-scores, in this case 5% of all the observations, with an absolute value greater than 2. However, a z-score with an absolute value greater than 3 would be highly unlikely under any circumstances. And we have seen there was one particular person who had a z-score of minus 3.5, and indeed this particular person had an extreme pretest score of 221 seconds and an extreme post-test score of 130 seconds. So obviously a huge fellow. Now, the next thing we can do is to get a further idea of what goes on with outlying observations is to carry out a logistic regression analysis. Well, not all of you will be acquainted with logistic regression analysis. A logistic regression analysis is something similar like linear regression analysis, but instead of having a quantitative dependent variable when carrying out logistic regression analysis, you have a dichotomous dependent variable. So if we use as dependent variable whether or not an observation can be considered as an outlier, and if we use as predictors of that particular dependent variable all the background variables that we have in our data file, like depletion, priming, gender, and age, then we can see if there's any significant association between some of the independent variables and the fact that we have an outlying observation or not. Well, in this particular case, none of the background variables like depletion, priming, etc. Succeeded in predicting whether a particular person would come out as outlying or not. So there was no association between the fact that we had an outlier and any of the background variables. Now, we decide to leave out the single extreme person with the z-score, the absolute z-score larger than 3, and we include all the other observations in the further analysis. Now, once again, we checked on the distribution of the group from which we deleted the outlier. With the outlier included, the distribution was very skewed and deviated significantly from a normal distribution. However, with the outlier omitted, the distribution looks far more normal. So here we have the original distribution, including the outlier to the left. You can see it looks fairly abnormal. And you can see that the tests of normality indicate a violation of normality. Now, with this single person taken out, it becomes a distribution like this. And now, of course, it looks perfectly reasonable as coming from a normal distribution, and the normality tests do not indicate any problem either. So this should alert you to the fact that single observations may truly distort the entire picture. And so if you have a single strange person, you can get a skewed distribution, a conspicuously low mean, and whatever. And taking out this particular outlying observation, everything suddenly looks reassuringly normal. Okay, so now how about the second assumption of doing analysis of variance, the assumption of homogeneous variances, that is to say, the assumption that the variance in the various populations are all the same. Let us compare the analysis on all the data with the analysis on the data with the outlier omitted. Now here we have the analysis on all data. And we can see that there's always a test of homogeneity of variance. This particular test, known as the Levene test, tests the null hypothesis that the population variances are all equal. And you can see this test is not significant at all. So it's reasonable to assume that given what we observe in this particular sample, so differences in standard deviations ranging from 17 to 29, these differences are not conspicuously large, at least not so large as to assume that at population level they are truly different. It's still reasonable to assume that at population level all variances and thereby all standard deviations are actually equal. Now if we carry out this analysis again, but with the extreme case omitted, the picture becomes like this. You can see that the Levene test is still not significant, but the p-value has become somewhat lower. It was about 0.45, it's now 0.15. So the situation is regarded as a little bit more extreme, but still it's not a significant picture what we're getting here. And the fact that this p-value has become somewhat smaller is related to the fact that we now have a single relatively large standard deviation, which is the value 29. All the other standard deviations are quite close together. And previously, as you can see over here, we had two standard deviations very close together, 17 and 19, and two other standard deviations also very close together, 26 and 29. And of course, the value of 26 has now suddenly been reduced to 15. And this is due to the fact that we've removed the single outlying observation. So once again, we observe that a single person may have quite a distorting influence on the entire picture. So we should be very alerted to the presence of outlying observations. Okay, so our data meet the assumptions of doing analysis of variance. However, suppose our data had clearly violated the homogeneity of variances assumption, then what? Well, I guess it's now 9:25. You probably want a cup of coffee or something. Shall we pause for about 15 minutes and no longer, because we need the time to finish all this important material.